So the other thing to be mindful of is that sometimes you might not be dealing with 100 milliliters of water. So for example, let's take a look at this. Okay, so let's still take a look at potassium chloride here. Okay, so we know that the 10-gram maximum is for 100 milliliters of water. Sometimes you might be asked, what type of solution occurs when you have, let's say, 21 grams of KClO3 in 300 milliliters of water. So this is really just a relative scale. So for example, this 10-gram maximum is for 100 milliliters, but you can adjust that. So let's say we had 3 times the amount of water. That means that I would be able to dissolve 3 times the amount of KClO3. So in 300 milliliters of water, the maximum saturation would then be 30 grams. Of course, we're still talking about the same temperature here. So 21 grams at that volume would then give us an unsaturated solution. Okay, so and the scale can go down too. So let's say instead of 100 mils, you're dealing with 50 milliliters. The maximum would then be half of that, right? So 5 grams. The other thing to be mindful of is that, of course, it changes as the temperature changes of the solvent. So for example, let's take a look at this point right here on the graph. At 70 degrees Celsius, we have a new saturation level. So at 70 degrees, I can dissolve 30 grams instead of 10 grams. So the temperature has a difference here as well. So a very common question is, can be comparing the different temperatures and then discussing supersaturated solutions. So for example, let's say we were to take 100 mils of water, heat it up to 70 degrees, we can dissolve 30 grams of it. And if we were to cool it down to 30 degrees, only 10 grams is the maximum. So if we had a disturbance that would saturate out or precipitate out the excess, we really are 20 grams above the current maximum. So imagine in that point, right, you have, right, so you have this. You had originally 30 grams dissolved. You cooled it down to now the new maximum is 10 grams. So what ends up happening is only 10 grams can fit in here, and the other 20 grams would eventually be solid at the bottom. Right? Whatever difference you have that you went over by is what would precipitate out or crystallize out at the bottom. So each line of this works exactly the same way. I mean, I know we focused on one molecule here, but you can look at any of the ionic compounds that are here and discuss the same types of things. So for example, the lead 2 nitrate, right, at 30 degrees is approximately 65 grams. So it's actually more soluble. You're able to dissolve more. The more of a solute you're able to dissolve, the higher the solubility. So as we go up on this curve, on this graph on the y-axis, the solubility is getting higher and higher. Right? So the lowest solubility would be the one that can dissolve the least amount. Now, I want you to notice that some of these lines kind of stop at certain points, right? Like the line stops. If you are ever asked a question that has to do with comparing compounds to each other, you cannot assume this graph is going to continue. Okay, so some students love to say, well, for example, I'll give you an example right now. So let's say I said, what's the ionic compound with the highest solubility at 90 degrees? Okay, so you would have to go up 90 degrees. Okay, well, the one with the highest solubility is this one right here, potassium potassium dichromate. So anyway, You cannot say, oh, it's going to be lead 2 nitrate because up here, lead 2 nitrate is going to be somewhere up here and that has the highest solubility. Absolutely not. You can only use the data that you have in front of you. You cannot make the assumption that the line is going to continue down that path. For example, for all we know, it could go straight up like this. It could continue and then go up. This one could go backwards. You don't know what is happening up here. There's no data for you to read that from. So you are not to extrapolate any data from these solubility curves. You only use the data that you have directly on, like a data point from this graph. Okay, so one of the worksheets that you have for part of the homework for this section has a graph very similar to this one. So there's different graphs, of course, that have different compounds on it. These are not all the different ionic compounds that exist, right? So they all work in the same way when you're reading them, but of course they can have different substances on it. So you're going to have a worksheet where it's going to ask you a bunch of questions to see how well you are, or I could just say to give you practice on how to read these curves. Okay, so this is just a recap. Remember that the points that are along the curve are the saturation points or the maximum quantities. Anything that is lower than that amount, right? So let's say this point right here is 15 grams per 100 grams of water. If I were to dissolve less than this, I have an unsaturated solution. So 15 grams, okay, well, if I only dissolve 10 grams, I'm below the maximum. If you do dissolve higher than that number, so if I had 17 grams that was fully dissolved, right, that would be considered to be a supersaturated solution. So what are some things that can affect solubility? So we talked about a few of these already. So the size of the molecule can have an impact. This is more so related to covalent structures, so things that are made up of nonmetals only. Okay, ionic compound, the molecule size does not have an impact. Typically, ionic compounds, though, will dissolve faster if you do have an increase in surface area. So let's say we have cubes, we have a crystal lattice structure for our ionic compound. If you were to crush this into a powder, like into smaller cubes or smaller forms, this will be more soluble. But in terms of the maximum, it will not affect, this will not affect the saturation levels. Okay. Temperature, we know, does affect saturation levels, and they have different effects on different substances. So for solids, if I'm trying to, so what we're talking about here is the solute. If you're trying to dissolve a solid into water, increasing the temperature will increase the solid solubility in general. There are always going to be exceptions to this rule. So for example, if you go back to this curve, most of these lines are increasing in solubility. Okay, however, there is an ionic compound here that is actually decreasing in solubility. So be careful. Anytime we're talking about trends, there's always going to be exceptions to that. So in general, yes, if we increase the temperature of the solvent, the solid solute will be able to dissolve easier or more. Now, if you have liquids, so a liquid that you're trying to dissolve into a liquid, so let's say we were putting, I don't know, you're putting milk into water and you want to mix it. Actually, the temperature does not really have a super big effect. So whether it's hot water or cold water, liquids can mix with other liquids pretty easily. Okay, unless they are different polarities. Remember, you still have to follow the like dissolves like rule. Okay, gases. So again, we're talking about a gas going into a liquid solvent or going into water. Now, when you increase the temperature of the water, the gas will actually decrease in solubility. So it's actually the opposite of a solid. So hot water holds gas in less than cold water. So for example, think of a pop can, okay? So here you have gas dissolved in a liquid, right? You have carbon dioxide gas, the bubbles that are inside of your can of pop. If you have a cold can, and we're talking about an open can, of course. If it's closed, the gas is not going anywhere. So if you have a cold can of pop, the carbonation actually will stay in the pop longer than if you have a hot or a warm can of pop. So you'll notice that if you've ever gone outside on a really, really hot day, you leave your, let's say you have an open can of pop, what will happen is it will go flat pretty quickly. But if you put your can of pop in the fridge, like if you open it and put it in the fridge, if you're not going to finish it right away, the bubbles will actually stay in there longer. And that's because temperature, what ends up happening is the particles, the warmer they get, so think of like the pop itself, like the liquid portion. If the liquid portion has a lot of energy, gas particles already have high amounts of energy. So what ends up happening is the liquid has high energy, the gas has high energy, so the gas eventually will basically just escape out of the can. So obviously if this is sealed, that's not what we're talking about here. We're talking about if there's an option for them to leave, hot water will actually hold the gas less than cold water. So this is just a graph, this is a gas solubility curve. And just to show you the trend that as you increase in temperature, right, the solubility of the gases will actually decrease in general. So pressure's impact. So pressure does not affect solids and liquids. It only truly has an effect on gas. So our last unit in this course is actually focusing on gas and chemistry involved with gases. So we're going to discuss this more in depth when we get to that. But essentially, if you have a gas, the higher the pressure is, the more you're able to actually have the gas go into a liquid. So remember, we're always referring to a liquid solvent here. So the higher the pressure, the more solubility. It's almost like you're basically forcing that gas to go into the liquid more. Whereas if you have less pressure, what happens is you have more space where there's air. So the gas will fill up that space instead of being forced to go into the liquid. So essentially, the less space you give the gas above the liquid, the more the gas will go into the liquid just because there's less space available. If you give the gas more empty space, the gas is going to fill up the empty space first. So the higher the pressure, the less space gas has, the more gas will go into the liquid. And exactly the opposite happens if you give it too much space.